Okay, so we will continue. Last time I thought I can already talk about the derivatives, but it seems like we still have something to say. So this will be like a last course in the theory of limits and continuous functions. So the first thing is about the composition of limit and continuous functions. So the first thing is that one might think that if so let me put it this way. This is wrong, okay? So I would say one might think that if the limit as x approaches a of f of x is L, and then as x approaches L of g of x, let me say as y approaches L of g of y, I mean it's the same. This is m, then one might think if x approaches a, then g of f of x, right, it will approach m. Why? Because x approaches a, so this will approaches L, and then g of something approaches L should be m, right? But this is false. So the problem is that so I will not talk about like the entire thing because I don't have enough time. But the problem is the limit. For example, the limit of this only says that for all epsilon bigger than 0, we can find some delta such that if x is close enough to a, right? Let's say if this is less than delta, then this will be less than epsilon, right? And for this one, if we want to show this is correct, then maybe we can choose some other letter. Let's say, then I want to show that for eta, we can find some epsilon, such that if f of x is close enough, I mean, if we want to show in this way, then we have to show that if this is bigger than 0 and less than epsilon, then g of f of x minus g of L, minus m will be less than eta, let's say. But the problem is that we cannot deduce from this to this. Why? Because we can only say from this, because it's a limit, right? And then everything we know here is that this is bigger than, we all know is that this is less than epsilon. So it is possible that this will attain L at some point. So if this is equal to 0, then this is wrong. Then this assumption is wrong, so that we cannot deduce the result, okay? So this is the main problem with this statement. So this is wrong. However, we still want to switch the order of the limit and the function. So it will be true if this is a continuous function. So now this is a proposition, so this is correct. So if g is continuous at let's say continuous at L, and then let's say the limit as x approaches a of f of x is L, then we can switch the order of limit and the function and the continuous function g, which is the limit of g of f of x will be equal to g of L. Okay? So which means that in this case, if we have a continuous function, then the limit of the continuous function g acts on f of x will be equal to g of the limit of f of x, given that this limit exists. Okay, so if this exists. So this is quite amazing, because for example, maybe we can choose the function g to be the exponential function, which we know is continuous. So if we want to know what is the limit as x approaches a of e to the f of x, then all we need to know is if the limit as x approaches a of f of x exists. So if this exists, then this is correct. Okay, so then we can switch the order of taking limit and take the composition of g. So maybe we can prove it. So to prove it, you will realize that this continuity is very important. Okay. So let's take a look. So because in the end we want to show that these two limits are the same, so we will first choose some epsilon bigger than 0, and in the end we want to find some small number such that if x is close enough to a, if the absolute value is less than that small number, then the difference between these 2 points should be less than epsilon. Okay, so then because this is like g of something, so we'll first use the continuity of g. So by continuity of g, we can find some delta bigger than 0 such that for all x, if let's say for all y, okay, because this will be in the place of f of x, which we will call y, okay, but it's the same because it's just used to be any real number. Then if y is close enough to L, let's say this is bigger than 0 and less than delta, then g of y will be close enough to g of L. So this will be less than epsilon. Okay. Now the point is that because this is continuity, so we don't need this bigger than 0, right? As we mentioned in the previous videos. So then we can delete this, and this will be important. Okay. Because we don't need this, then we can use this limit, right? Because the limit will say that because of, or let's say since delta is bigger than 0, and we also have the limit as x approaches a of f of x is L. So we can use this delta to find some, let's say some eta bigger than 0, such that, or let's say maybe we'll call it delta prime bigger than 0, such that for all x in R, if x is close enough to a, let's say less than delta prime, then f of x will be close enough to L. So this will be, this should be bigger than 0 because this is the limit, and then this will be less than delta. Okay, and now basically we're done. Why? Because we want to show if x is close enough to a, right? So let's assume that x is some real number such that the distance to a is bigger than 0 and less than delta prime. Then by star, we know that f of x must be very close to L. So this will be less than delta. And now we can call this f of x as y. Okay, so if we call it y, then you'll see it satisfies the condition absolute value of y minus L is less than delta. So then this will say that g of y will be very close to g of L. But here y is f of x. So this says that g of f of x will be very close to g of L, right? Less than epsilon. Now we have shown that for all epsilon bigger than 0, we can find some delta prime bigger than 0, such that if x is close enough to a, when this absolute value is bigger than 0 and less than delta prime, then g of f of x, right, will be very close to g of L. So by this we have shown that the limit as x approaches a of g of f of x will be equal to g of L. Okay. So this is the proof, and then what's important is that we should know that we cannot just switch the order of the limit and in the function g in general, but we can switch if this function g is continuous. So this will quickly give us a corollary that I will not prove, but you can see very quickly that if f is continuous at a and g is continuous at f of a, then as you wish, g of g composed with f will be continuous at a. Okay, you just play with it, because in this case you can switch the order. Maybe we can just proving as fun. Okay, so g of f of x, because g is continuous, this is because g is continuous, we can make it into g of the limit as x approaches a of f of x. But also here f is continuous, so then this will becomes, by the continuity of f, this is g of f of a. Okay, and we're done. Then this says that for all x, then g composed with f at x is equal to the value at a, and we're done. Okay, and now we should also talk about some important limits about trigonometric functions. Okay. So the first important, so these are some limits about the trigonometric functions. The first thing is the limit as x approaches 0 of sine of x over x. This will be equal to 1. And then we just take it for granted, okay? Which means as x approaches 0, the sine of x is just approximately equal to x, okay? So by this, what I mean is that the sine x over x will be approximately 1, or it will converge to 1, okay? This means they are equivalent infinitesimal, because as x approaches 0, this will approaches to 0, and this will approaches to 0. In general, we cannot compare any two infinitesimal. We have to be very careful. And later, we will use L'Hopital's rule to justify which is bigger. And in some case, they are of equal size, just like here. They're equivalent. So the quotient will go to 1, okay? The quotient will go to 1. And I will not show a proof because the most rigorous proof actually require you to define the sine function in a correct way. And then the correct way is to use a series, okay? Is to use series. Just like, I think it starts with x, and then x minus 1 over 3 factorial x cubed plus, yes, something like that. Otherwise, it's all like circular argument. But now let's just take it for granted. So we'll take it for granted, and then we will show quickly that so this is an exercise. The limit as x approaches 0 of tangent x over x is also 1, which means as x approaches 0, the tangent of x is also approximately x. But why is that true? Because we know that tangent x is simply sine of x over cos of x, right? And then as x approaches 0, cos of x is not an infinitesimal, which means it will not converge to 0, because cos is also continuous, and the limit of cos of x as x approaches 0 is cos of 0, because it's continuous, which is 1. Okay? So if you want to write it in this way, then you can say cos of x is approximately 1, because it will converge to 1. So we can simply rewrite this as sine x over x times 1 over cos of x. And we know that this will converge to 1 as x approaches 0, and this will approaches also 1 as x approaches 0. So this will converge to 1 by the product rule, right? This is by the product rule. Because the limit of the product would be the product of the limit if both limit exists. And, okay. So this is also easy to understand. But this is something, but now this exercise might be slightly trickier. So this asks you to prove that the limit as x approaches 0 of 1 minus cos of x. Okay, the importance of 1 minus cos of x is that as x approaches 0, cos of x will approach 1, right? So then 1 minus cos of x will approach to 0. So then we want to know which is this equivalent to in terms of infinitesimal, right? We want to find something that is very familiar such that this limit is 1, right? So we will use some monomial, which is polynomial with only one term. So in this case, this is 1/2 x squared. And we cannot just erase this 1/2, because otherwise this one also needs to be changed. It has to be 1/2. So this will be very important, and you will see why this is 1/2 when you have learned Taylor's theorem or Taylor expansion of the cos function. But now we will just prove that this limit is equal to 1. So why is this true? So we cannot do it directly, right? So we have to use some trigonometric identity. And then the trick here is that we can multiply both sides by 1 plus cos x, right? So if you multiply by 1 plus cos of x, then in the denominator, this will converge to 2. Because x approaches 0, so 1 plus cos of 0, which is 1 plus 1, will approach to 2. So then they can cancel out, right? This 1/2 cancels out with 2. So let me write in this way. So for the denominator, it is already x squared. The reason why we can take this limit is because the limit exists, okay? And also the other one will exist by our following discussion. And now this will be equal to 1 minus cos square x, which is by a simple trigonometric identity equal to sine squared of x, because sine squared plus cos squared is equal to 1. So this is sine squared of x. And I think you can find, so this should be sine squared of x, which is sine x squared, okay? Let me just write in this way. So then you can find a pattern. This is simply the square of the limit of sine x over x when x equal to 0. But this is equal to 1 by the previous, by the assumption, or by something we don't want to prove, but we just take it for granted, then this is equal to 1. So this proved that as x approaches 0, 1 minus cos of x is approximately 1/2 x squared. Okay? So we can use this to do some simple exercise. So for example, one might be interested in, what about 1 minus cos of x divided by x? Then I claim that this should be 0. Why? Because for that, this is just approximately 1/2 x squared. So then this will be cancelled out, and then you will get this is 1/2 x, but x approaches 0, so this is 0. But we have to prove it rigorously. So let me write some word. But the intuition is correct. So we can write this as the limit. We can first play with this 1 minus cos of x with 1/2 x squared. So we can divide by 1/2 x squared, and then we can multiply by 1/2 x squared. So then you can see this term will go to 1, right? And then this term would be, so let me write it in this way. So it will be the limit of the first term, which we know will converge to 1. And the second limit, we can write in this way because just in one step, we will show that the limit exists. So this will clearly converge to 1. Clearly converge to 0, and this will converge to 1. Or the limit is equal to 1 times 0, which is 0, and we're done. Okay? So this is basically because the numerator is approximately 1/2 x squared, while the denominator is simply approximately it is equal to x. But then when x approaches 0, 1/2 x squared approaches to 0 much faster than x. So then this will be 0, right? Because if you look at the graph, then 1/2 is x squared is like this. It converges to 0 very, very quick. But x approaches to 0 very, very slow. Okay? Very, very slowly. So that's why this should be 0. And you can prove it rigorously by just cancel out, and then you will have some x here. Some multiple of, I don't care about the multiple, but it's some multiple of x. So it will converge to 0. And now we can we can do some exercise using this limit. So now we can find the limit as x approaches 0 of sine squared of 4x divided by tangent of x squared. So now we want to know that so first the observation is that when x approaches 0, then 4x will approach 0, right? And also x squared will approach 0, which means we can use the equivalence of the infinitesimal for sine and tangent. So now we can basically use the sine of something. Let's say sine of y would be approximately y as y goes to infinity, and then tangent of z will be approximately also z. I mean here as y and z goes to 0. We have to emphasize this because we want to take the limit as it approach some point. Okay. So now this means if I want to do it rigorously, then this limit should be, we should compare this sine square of 4x with 4x squared, right? And then we multiply by 4x over this tangent. But also for this tangent, this should be 4x squared. And then we want to divide by tangent of x squared, but then tangent x squared should be equal to x squared. And then we must put x squared over here, right? So then we multiply 4x squared and divide by 4x squared. We multiply by x squared and then we divide by x squared. So the point of this is that in this way, we can cancel out the term of sine and tangent completely, because the first term is the limit of sine of 4x over 4x to the power of 2. We will just take the square. And then the last term is x squared over 10. Oh, so it is x. It's just x squared over tangent of x squared, which will also converge to 1. This is 1. This is 1. The last term is simply the limit of 16. So this is times 16. So the result is 16. So intuitively, to prove this, you can just simply say that this sine of something that approaches 0 is approximately just 4x. And then we need to take the square, so this is 4x squared. And tangent is approximately also this value when it approaches 0, so this is simply x squared. So then we can cancel out x squared to get this is 16 when x approaches 0, okay? But I have to say that sine of x is not equal to 0, right? I said that it's approximately x when x approaches 0 in the sense of limit, right? The limit of sine x over x as x approaches 0 is 1. So similarly for tangent x. And also similarly for 1 minus cos of x with 1/2 x squared. Okay, then I think we are